glad to have been able to convince Dejan for the second time now to speak for us. So he was presenting a wonderful talk at the Ross workshop at Supercomputing as a keynote. And now for the benefit of all us as an online audience, as well as an offline audience in the group downstairs, I'm so glad to have Dejan present again on this wonderful topic of heterogeneous serverless computing. So Nikolai is going to introduce him a little bit more formally. So thank you, Dejan.
Thank you, Torsten.
Thank you.
Got 2 talks for the price of 1.
Yeah, thank you also, Torsten, and thank you, Dejan. So Dejan is a distinguished technologist at Hewlett-Packard Labs, where he leads research on future architectures and is the PI of the heterogeneous serverless computing that spans all of HP Labs. He received his bachelor's and master's degrees from Belgrade University and his PhD from the University of Kaiserslautern in Germany. He's received numerous awards, best paper nominations, and so on. He is an IEEE fellow and an ACM distinguished engineer. He is also the former president of the IEEE Computer Society. He's led large industry and government and academia collaborations, such as Open Cirrus for the HPC and Cloud program, and the New Operating System for the Machine program. Numerous other awards and so on, but let's just let Dejan go ahead and take it away. And thank you, everyone.
Thanks again, Torsten and Nicole, and thanks for having me here, and thanks everyone for joining. Indeed, I'm the PI on this program, but I cannot overestimate the benefits and contributions of the immediate team that is listed here, and then a bunch of other people who help formulate this program. So in this talk, I will first give you the broader context, how we look at the broader area of high performance computing, AI, machine learning at HP, and how we see the world moving in what direction. And then in the second part, I will focus on what we've actually done. Also want to point out that even though we've been running it for maybe a year plus, we still consider it in early phases. But like most industry, we're always pressured to deliver technologies that we can transfer. So there are certain nuggets that are already now transferable towards products, because that's what we do in industrial labs. We all have been recently motivated by the first exascale computer delivered. And there's anecdotal evidence that about 12 years ago, at an internal HP at that time, Hewlett-Packard, we were one company, together with a few colleagues, we wrote a paper on exascale where we widely overestimated the size of the exascale computer. I think we were in multiple hundreds of cabinets compared to what was delivered today. And that's the beauty of trying to predict things. The Frontier that was delivered recently to Oak Ridge was pretty successful by multiple dimensions. Not only that it was the first on the top 500, but also it got to become first in Green 500, as well as on this HPL AI list. And there's some underpinning that influenced us in our program. Specifically, the core of this computer is comprised of CPUs and a large number of GPUs, which, again, we completely underestimated the evolution of GPUs 12 years ago. And then the importance of the slingshot interconnect. At that time, neither SGI nor Cray, in this particular case, very important for slingshot, were there. So things have changed quite a bit, but what remained the same were the targets, exascale, and then the power consumption. And that's what has been driving us in our program as well. You've seen this picture many times, so I'm not going to talk about end of Moore's law, Dennard scaling, etc. Would just like to point out that it's really what we do with these computers. So if you think about the scale of the models that continuously grows, and then when you multiply that with the number of data sources that are exploding at the edge, at the cloud, everywhere, and then the shrinking time to action, because it's all about what are you going to do with all this data that is coming in. And so that's what has been driving us as a motivation. When we look at the future, we see the trends of this rise of non-x86 processing, and I'll come back to this a little bit later. We see the requirements to enable this heterogeneity as flexible, streamlined, and abstract. And you can read what this means, but it's pretty similar to what I understand is happening in your lab, but also at ETH, and then broadly in industry. We are moving towards this conversion or this congregation of high-performance computing, AI, and data analytics with all the features. Now, what it means and what people usually ask, so are you really going to change all these millions of lines of code that exist in various applications? That's not going to happen because it's too costly, too complex, and really not needed. What is happening is that new applications are being developed that use these existing applications either in the existing form or potentially converted to be delivered as a service of some sort. And then new aspects are added for data analytics, for AI, and other applications, in general data science. When we try to deliver that, what it really means is trying to, for practical purposes, to have a similar kind of architecture that goes all the way from edge through cloud. At HP, we have private cloud, which is called GreenLake, through large memory systems like Dragonhawks, Superdome series of machines, XSGI and XApollo machines from HP, then through exascale systems like Frontier, El Capitan, and other future systems that we and the rest of industry will deliver, and then whatever comes beyond. And that what comes beyond is probably a little bit of unknown. There's a lot of investment in quantum computing, a lot of investment in new optimized AI machine workloads. Some of the architectures that we still can't predict, but we are forced to anticipate how they will look like so that they can fit with the rest of the architectures, because no new architecture will replace everything else. We already know that. We still have mainframes in large banks that exist there. There are not too many, there are few, but they still exist. COBOL is still used. So there's a lot of legacy that will continue to be used. It may eventually phase out, but in the foreseeable future, there's not going to be dramatic shift. There'll be addition of either quantum or quantum-like, but we'll have to make it work with existing hardware. What is interesting, though, is what they call democratizing AI. And we have these completely inverted behaviors. If you remember, up until recently, we had these large computers that had accelerators added to them in the form of client-server model, where large computers were servers, and these accelerators served as clients, as serving computation that was orchestrated by a large computer. With the emergence of new super accelerators like Cerebras, we have this inverted behavior that Superdome machines, very large scale memory machines, were really required to deliver the data to feed these Cerebras accelerators. So we'll see these kinds of inverted behaviors more and more as new types of customized, specialized accelerators are introduced to offset for the end of Moore's law. I found it extremely intriguing. Now, for a few of us who were there in 1980s, even before, we've seen this surgence of new processing elements. In the past, there used to be Motorola, IBM, RS6K. I remember working on that and other IBM machines. There was MIPS, there was Digital, there was Sun. Some companies still remain like Fujitsu. I'm not sure to what extent Hitachi is now producing processors. HP got split into HP and HP Inc., where HP continued on the path, but we don't produce our processors. Over the years, maybe 10, 20 years, the market forced this plethora of different processors to converge into only a couple of architectures. We have Intel and AMD delivering x86 architecture and then ARM architecture. Because market really requires standardized deployment. They require common architectures because there's so much software that can't afford to port to all these different architectures. And I witnessed a variety, not just of compilers, but operating systems, tools, all kinds of tool chains that had to be ported to these, which got simplified dramatically with x86 and then only ARM largely on the client side. Now we're in the similar situation. And if history taught us anything, it is that they will converge, eventually hardware and then also software. And the jury is out what the convergence point will be. Is it some sort of RISC-V or some other open architecture? And when exactly it will be, but we all think it's inevitable. So standardization always eventually wins. Innovation drives these 1,000 flowers bloom, but then it goes towards standardization. And I pointed out the programming because hardware is at the bottom. It's really, or however you want to look at it, tip of the iceberg, and then underneath are all these programming efforts that are there. In order to program these accelerators, but not only accelerators, but different types of memories, requires new programming models. Up until recently, we largely, and Torsten was one of de facto leaders of MPI, and then we had also multi-threading as an alternative. The question is, what is the third programming model? And then there are all kinds of other runtime interfaces like OpenFEM for fabric attached memory, different types of tools for accelerators. At Labs, we've done collaboration with a number of universities. One is UIUC, and the offshoot thereof, Sitao Huang, who is now professor at University of California in Irvine, who, while at UIUC, developed Pylog. And through that tool, which is Python interface, and I'll talk a little bit more about it later, we observed that there are these silos. So when you have different types of CPUs, different types of accelerators, GPUs, FPGAs, a lot of things are happening in isolation. So have source code only for one of these, you have compilers, and in particular, I want to point out optimization because most of the effort really goes in optimization. You develop source code, you can tweak it, debug it, but then to optimize it takes a lot of time and effort. And so the more we can have commonality across these different architectures, the more savings we can have, the more benefits. So if we can have the common source code, if we can have the optimized high-level synthesized code, and then potentially we may have to diverge into architecture-specific optimizations and then eventually deployment. Eventually, we'll have this unified hardware as per few slides ago, but until then, we need to make sure that we take advantage of commonality as much as possible. In terms of deployment, we like to think of the need for federation. That federation happens both in the cloud and on-premise architectures, and then also at the edge. And you can have federated IoT at the edge, you can have federated clusters, federated clouds. There's a lot of benefits and a lot of rejection thereof, because obviously every individual cloud provider wants to maintain their customers for themselves. But customers, on the other hand, want to have the freedom to run on multiple clouds and, you know, take the advantage of competition. And the same is true for clusters. Sometimes It's simply to be able to scale from your own supercomputer, no matter how big it is, to other supercomputers or private clouds. And then there's obviously vertical federation, where you want to federate sources of data, Large Hadron Collider, for example, to federate with either private data centers or private clouds, or even public clouds for certain kinds of computation. And the same is true for large microscopes, manufacturing, wind centrals, MRI, robots, et cetera, et cetera. And then you can have, obviously, diagonal federation, all kinds of other federation you can think of. And by the way, there's a lot of, I put links here to various papers that go into more detail about this and previous work. So this was the high level description. I spent about 15 minutes discussing it. Now I will switch to what we do with heterogeneous serverless computing, which was motivated by this large landscape that I was telling you about. As I mentioned, it is the result of a number of direct contributors to the work, but with support for even a larger number of people who provide the technical, business, and other perspectives, some of whom are still with us, some of whom have left. The motivation for heterogeneous serverless obviously lies in these two first words. And I spent a lot of time speaking about heterogeneous accelerators. You're already familiar with a number of them. Some are still there, some are even going away. Competition is taking the toll. And then on the serverless side, our motivation was observation that as you go from different types of virtualization techniques, from bare metal clusters through VMs, containers, and then to functions as a service or serverless, you have increasingly easier development. From clusters where you have to think about the hardware, you move to VMs where you drop the hardware altogether, but you still have to think about operating systems. With containers, you drop operating systems. And then when you move to functions, you drop the whole development environment. You just fire off these functions, which take care of scale outs and updates and other techniques. On the x-axis, you can observe the increased granularity or compartmentalization. In clusters, you have access to the whole hardware. With VMs, it's a subset of the hardware. With containers, it's a part of a single operating system. And with functions, you have very fine granularity. And so consequently, as you deploy things, as you scale out, there's opportunity and the real motivation for us to match this fine granularity of functions, certainly finer granularity. They could be coarser granularity, but they have opportunity to be very fine granular, both in terms of level of abstraction, as well as time, because clusters you usually deploy for 3-5 years. VMs can be up there running for a year or more. Containers, we're talking about minutes. Functions can go all the way down to seconds when they execute something and then withdraw control to other invocations. And the same is true with accelerators, because they deliver huge number of cores. So there's this intuition and our motivation. Can we really match the fine granularity of accelerators as a hardware abstraction with the fine granularity of virtualized function as a service? And are there benefits thereof? The analogous observation was when you want to fill up the jar, you fill it first with big stones, then you fill it with pebbles, and then you can fill it up all the way to the top with the sand. So this fine-grained sand that could be executed as a function of service on fine cores of accelerators is what motivated us to observe whether we can achieve better performance for users and better performance efficiency for providers, be it the cloud providers or the owners of the clusters, supercomputers, private clouds, et cetera. And there's also the whole market, which goes in terms of adoption of functions as a service, and obviously accelerators, which are still blooming. When we think about this Gartner curve, you can see that there's evolution and different types of accelerators, all the way from, you know, disillusion in the beginning through disillusionment, all the way to adoption. And then when we think about serverless, Gartner put it there, going down towards disillusionment. We think that heterogeneous accelerators are inevitable. We used serverless, specifically function as a service, more opportunistically, because there are other types of virtualization that we could have also easily used. And if serverless does not take off eventually, it should not be a problem to switch to others, maybe not with all the benefits of fine granularity, but perhaps fine granularity support could be instilled in some other virtualization techniques. So I will just read you this one sentence. We spent about half an hour or more, Kirk Bresnik and I, drafting it, and people still complain about it. But in a gist, this is what we think HSC is. This heterogeneous serverless computing is workflow optimized, and workflow is key here, that we start from the workflows, not from any other unit of computation. Architecture that is inclusive of or compatible with the public cloud, meaning we should be able to run anything that runs in the cloud, but also for a set of workloads that is broader than what the public cloud can support today. And when we say broader and cannot support, we're thinking of very large scale, tightly coupled parallel applications that are not suitable for scale out public. Now, obviously, you can put the whole frontier behind the public cloud interfaces, but that's not the same. The business model of cloud is overutilization of their hardware architecture, which is typically commodity servers, although they increasingly more are putting high performance computing, the low end high performance computing. Well, we advocate that we can, in the future, going forward, also run as HSC more tightly coupled large-scale workloads, which are in the domain of not only HPC, but also AI, machine learning, and data analytics. For those who like graphs, here's how we came up with, because people will ask me, why HSC, why HSC? So here's how we thought of it. We start with growth of data, which resulted in broad AI adoption, data analytics. Then together with traditional HPC and end of Moore's law, these all motivated heterogeneous. Then together with new scalable apps, AI, data analytics, with DevOps experience, with composable modular code, resulted in the need for serverless. And then heterogeneous serverless together with vertical integration and efficient resource utilization resulted in this new computing architecture. So that's how we came up with it. We think that HSC, the model and architecture, is required because traditional apps are embracing AI, data analytics, and HPC. They're moving more from traditional cluster and supercomputer model to delivery on-prem, from on-prem to the cloud. We spoke quite a bit about standardized solution, interoperability, which aligns well with the Internet of Workflows. So if you already have workflows deployed in the cloud, you can simply start invoking them while you can still execute tightly coupled HPC applications on-prem. There's reduction in operational cost, at least there's a promise via serverless, because it's already there deployed, you just need to invoke it. And it raises the level of abstractions towards low code, no code. Not entirely there, but you don't really need to think about what is in function, at least at the first order of approximation. Once you start optimizing performance, once you start scaling really to the large scales, you need to think about all of these. And then there's this precision in time and resources. How do you match the quantum of workload to quantum of resource? Our goals are focus on customers, on end users, developers, and providers. I already mentioned a little bit, but for end users, what is important is the seamless scalability and fluidity of new applications. So if you already have in the cloud deployed these functions, then you can seamlessly scale out and invoke them. For programmers, you have increased programmer productivity if you already have these deployed functions, and as I was saying with analogy of these jars, you can have improved performance efficiency. So these are our focuses to seamless scalability, programmer productivity, and performance efficiency. And everything we've done was focused on these three goals for end users, developers, and providers. And providers, it could be yourself. If you have your own supercomputer, you really want to fill it up as much as possible. You don't want to use only half of it. And the more you can fit in your users, because in many ways, these large Department of Energy labs in US and in the rest of the world, they are providing it to their scientists, and they want them to be used as much as possible. And I think this is one of the last slides of generality, then I'll go more into technical details. So if you think about business landscape, I think you are probably all familiar that complex worldwide problems, and there are many. You've seen with the COVID, there was requirement to decode the genes with global warming, understanding how things change, climate, supply chain disruption. All of these are growing demand for HPC, as well as data analytics. And what is happening is there's a broader and broader adoption because there's more and more users outside of traditional HPC that are looking at it. And then there's AI machine learning, which transforms computing all the way from cloud to edge, where you do a lot of analytics at the edge and then all the way to the cloud. So that's on the demand side. On the supply side, we mentioned over and over continued heterogeneity, workflow composition that helps you leverage existing workflows, and then as a service delivery. What is transpiring all of that is, especially because of the cloud delivery, there's a lot of closed innovation. As good as cloud is, because it democratizes access to computation, the issue becomes that once you have hardware and software behind the cloud interfaces, you can at leisure make changes, as long as interfaces remain the same and there aren't different behaviors. And that's threat to that vertical integration, which optimizes performance, improves their performance efficiency, etc., is really threat to innovation because it's closed. And they don't want to expose it because once it's exposed, people will start leveraging it. So it's not beneficial to them. But it's not good for the community because innovation is closed. And major silicon vendors are doing similar. If you think about CUDA and other things, even though the interfaces are open and available, you are still locked into their model. And accelerator startups are following the model. They are really developing many proprietary interfaces that they don't need to because they think it's a value differentiator. Most of them should really be open up. And we have a number of papers discussing this and even the podcasts. So as I was telling you earlier, our hypothesis of this whole work, technical hypothesis, is can we match fine granularity of accelerators with that of serverless? That is short time to execute, service lifetime, and size of deployed code or the hardware architecture. So to prove this hypothesis, we've done one of the experiments. We're doing many more. I'm just reporting one. We tried to run matrix multiplication and try to do it on VMs and on serverless. And we've demonstrated that for very small granularity, we are achieving a much better relative increase in throughput. And I asked them to create, my colleagues, to create this graph because it may not be as obvious from this one. It is because the gradient is much higher here, but this is very, in an obvious way, showcasing this. Again, this is just one very primitive proof. We have many more that we've since done, working on another paper, and this one was done on CPUs and GPUs. We've also repeated some experiments on TPUs, other accelerators, and even on some sort of quantum infrastructure. So to deliver heterogeneous serverless computing, here are the actual efforts that we pursue. we're focusing on programming for heterogeneity, and I'll, by the way, talk in more detail to each one of these. Programming for heterogeneity is attempt to both hide the heterogeneous aspects, which complicates programming, but at the same time enable access to distinct features. Then we have the benchmark framework. As we were developing the rest of the components, we realized that it's really important to have consistent benchmarking that can do the same type of experiments, not only on different hardware, but also on different serverless frameworks and platforms. And then we have used a number of workflow managers. For workflow managers and for platforms, early on, we decided that there are multiple thereof. So we didn't see the value of creating yet another workflow manager or yet another platform. I think you should be proud of RFAS. And we look closely at it, even though we started working initially, at least, more on Funcax, Fusion, and Native. Then the next components is focusing on accelerated communication architecture. We realized that different accelerators have different ways of deployment, different hardware, different interconnects, different shared memory and other types of communication. And especially for very large scale models, as you deploy them, it is critical to optimize what we call this accelerated communication architecture. So that is our lowest level software that we've been focusing on. The other important component is energy aware scheduler. And we call it both energy and accelerator, heterogeneity aware scheduler. We're trying to, as much as possible, leverage the differences in these accelerators to achieve optimized performance and performance efficiency, and then energy usage. And so that's the focus of this component. And then this one almost predated the whole HSE program, but it was so successful and it raised so much interest with everyone. And even though it seems like it's been there forever, application performance prediction really never resulted in widely adopted tools. A lot of people published about it. There are tools, but they are unique to either platforms or hardware, etc. And especially for the new landscape where you have accelerators, we have AI applications, machine learning, we have data analytics, there's not sufficient amount of focus on application performance prediction. We're also using other tools, or other tools can use us, such as sustainability dashboard. We are leveraging our Cirrus, which is our HPC cluster or private cloud. We do a lot of Green Lake, which is our private cloud, general purpose private cloud, as opposed to Cirrus. We are leveraging public cloud. We work with telcos and a lot of on-prem hardware that we do. So this is our landscape. HSC is in green, and these half blue, half green is where we leverage existing tools, whereas full green is what we have developed. So for the rest of the talk, I'll focus on these individual components, and I'll try to leave at least 10 minutes, if not more, for some Q&A. So let me tell you a little bit about what this PyLog, or what we call HSC programming for heterogeneity, is. And as I mentioned, this is joint work with Professor Sitao Huang, which started maybe 4 or 5 years ago. We have a number of publications on this, and Professor has his own, and you can also pick up that code. It has been running initially on CPUs and FPGAs, and that was motivation. This large gap between hardware and software abstractions between CPUs and FPGAs. And that was even before we were confronted with a plethora of other accelerators which only exacerbated the problem. In the meanwhile, we've added GPU support. So if you think about how you develop FPGAs, you have very high level tools, and then you have the very low level deployment, and there's the huge gap between the two. What Pylog does is using annotation, Python annotation. It enables you to do all kinds of definitions for how you want to deploy things, what kind of concurrency, what kind of workflows like these that I showcase on the right. Overall, we're trying to also focus on optimizations, which is really the key thing, because you can do all kind of gymnastics with compilers, but most of the efforts are taking place in this optimization layers. And as I said, we're extending this tool from CPUs and FPGAs to GPUs and other accelerators. Through this, what we want to achieve is improve developer productivity, fewer lines of code, easier debugging, easier system integration, because it has a common code base, both for the deployed code that runs on FPGA and how you use it. And then also really important, easier designs, design space exploration. How can you explore what are the real parameters? How do you configure this hardware, deploy it, how you use it at the top, how you integrate it with other tools. So really powerful. We are almost, as I said, at the tip of the iceberg, but it's extremely promising, and that's the top of our stack. And you can see some examples of code. The next one is serverless frameworks. We started collaborating with Ian Foster on this. What we've done is we tried to compare in different approaches, including Kubernetes, which kind of snuck in itself. It's not serverless frameworks. Serverless framework, although we've been using it in that way and wanting to compare it. So our team members, because they used it, they stuck it in. But for us, of importance is really heterogeneity support. And you can see that while all of them run on CPUs and most of them run on GPUs, there's very little support for FPGAs and NICs, smart NICs. Not all support auto-scaling, which is important for us. Few support multiple container technologies. Not all support HPC. The RFAS is distinction here, as is FunkX. Not all are open source, which is important for us, but I think they're all going in that direction. And then maturity. FunkX has been there for a long time. I think inherited a lot of experience for Globus, and Kubernetes has broad deployment. And then in terms of responsiveness, where I think RFAS really shines, not everyone is focusing on that part of design space. FunkX, for example, is focusing on second level response times, whereas RFAS is looking really down at the data center level communication using RDMA. So eventually, as we look more closely into tightly coupled application, we would really like to leverage some more RFAS. And then everything else is somewhere in between Fission, OSS, and Kubernetes. We'll continue to explore them, but we're really trying to leverage them. And I don't think there's one clear winner, at least not at this time, because they are really covering different problem spaces. I mentioned and raved about application performance prediction. It is motivated by the fact that if you have one application and you want to run it in the cloud, you have to spend a lot of time to identify what is the best configuration. Are you going to have small, medium, large clusters in the of the virtual CPUs? How much memory, et cetera, et cetera. So what this effort did is it made observation that, and this first three pairs are really indicative that for the first one, it is beneficial to go all the way up to 8 virtual CPUs. Beyond that, you can go and you don't have additional costs, but you have all the benefits. For this one, you don't want to go beyond 8. And for this one, the optimal is 1. So you really need to understand your application and then how it scales and what are the sweet spots for deployment in the cloud. The way the team in American University of Beirut, and this gentleman is also a professor, Isaac El-Hajj, is also from UIUC. He's also a student on Wenmei Hu, who we worked closely with for a number of years, as I mentioned. They started from one application and then they profiled it extensively, so much that they were able to produce a fingerprint. Then they've taken these fingerprint application, have done classifiers to identify how it scales. And using regression model, they came up with this performance configuration curves. And what it together was able to demonstrate is that if you have one application which is fingerprinted, you know how to deploy it, and you also know what will be performance for any other configuration. Because as the prices change in the cloud, especially, these curves change. So you want to have the functions which will enable you together with fingerprint to decide what is the optimal, both in terms of performance and price configuration that you're going to use. They've done I think about 80 different applications, and were able to come up with about 80 configurations. And I think they achieved pretty good error rates. I think it goes on average about 14%, but the maximum is somewhere, goes all the way up to 40 for a small number, but can be very low for others. And it depends from application to application. The real benefit will be shown once we start using it in various use cases. And there are some publications for this. For the workflow manager, what we try to do is also repeat these experiments, largely exploring what are the benefits, and I'm going to speed up a little bit to leave some time for the Q&A. What are the benefits of cold versus hot replicas? Showcase that for different applications, we get different benefits. Again, really important as we run it to understand the behaviors. Benchmarking framework enables you, and I know Torsten will love this, to not only do the different programmatically reconfigurable workflows for testing, but also to insert programmatically different amount of noise. As I said, it is used for doing benchmarking of both hardware as well as different frameworks, serverless frameworks, and even applications. We're trying now to connect it to various simulation platforms and other tools like schedulers. And speaking of schedulers, we started focusing on this heterogeneity and energy waste scheduler. The way it works, we have all these tasks that come into it. We do with reinforcement learning feedback loop, we have the performance behaviors, and then we also fed into the loop, which hasn't been described here because at the time it wasn't there, but now we're adding application performance prediction in it. So together with application performance prediction, and due to the changes, this reinforcement learning really helps. What is happening here is for different application, we can trade off the time, duration of execution for the energy usage. Sometimes you can achieve both, in other times it's the true trade-off. And then for the accelerated communication architecture, we do it both with Wenmei Hu, who I apologize I didn't list here, and Professor Deming Chen. We've been trying to look at, with FPGAs and GPUs, how can we map this communication architecture for very large scale models, and what kind of benefits do we achieve? And we do it for different types of communication, broadcast, all gather, reduce, et cetera, and different. And we've been expanding it also with Technion. We just started this collaboration, too early to talk about. I'd like to close with this Internet of Workflows, which just depicts how we use all of this. So we can have things collected from the edge, different kind of information that triggers these Internet of Workflows that then gets deployed on different either supercomputers, on-premises, cloud. And our accelerator communication architecture helps there. Our heterogeneity and energy-aware scheduler helps deploy it and run it at various appropriate places. Workflow managers orchestrates and collaborates together with schedulers. Our programming for heterogeneity enables generation of these workflows. Benchmarking frameworks tests it all, and then application performance prediction also helps therein. For the DevOps, we're focusing on these first two top tools, and together with policies, we can improve DevOps. For sustainability, we're focusing on these layers: benchmarking frameworks, performance prediction, workflow manager, energy-aware scheduler, and together with policies, we're able to manage it. So in summary, let me repeat this one single important sentence: what HSC is. Heterogeneous serverless computing is workflow optimized architecture, which is inclusive of, compatible with the public cloud for a set of workloads that is broader than what the public cloud can support. We have proved and continue to prove our HSC hypothesis of matching fine granularity accelerators with that of serverless. And we do that increasingly more so for different accelerators and for different hardware. And at the moment, what we're working on is towards productization of individual HSC components and also combining them. So here are our components, and thank you very much. We have about 10 more minutes. If you approach me, I can send you some papers and you can follow me on social media. Thanks.
Okay. Thank you so much, Dan. Before we move to questions, just a quick announcement that our next BCast and last BCast for the year will be on the 15th of December at this same time. We'll have David Clark from AMD.